This is a short introduction to the paper titled Shapley Values of Structured Additive Regression Models and Application to RKHS Weightings of Functions. Interpreting machine learning models and developing rigorous theoretical foundations are two crucial goals for advancing AI systems. This paper addresses these goals with two key contributions. The first is a novel algorithm, StarShap, for efficiently calculating the Shapley values for a broad family of models. The second contribution is an improvement to the understanding and applicability of a recently introduced class of models, RKHS Weightings. We also ran various experiments to assess every model and algorithm introduced in the paper. The first contribution concerns Shapley values, a value attribution method widely used in machine learning. While theoretically justified, their main drawback is the exponential computation time. Except for very small models with few variables, they are too slow to use in real-time applications. For instance, doctors cannot wait for the interpretation of model predictions about the health of their patients. Recent work has been done in two directions to solve this issue. On one hand, exact algorithms have been developed, such as TreeShap or LinearShap, which can efficiently calculate the Shapley values for some specific families of models, like decision trees or linear models. On the other hand, approximation algorithms, like kernel Shap, can estimate the Shapley values for any model at the cost of obtaining inexact values. With this in mind, we present StarShap, an exact algorithm which can efficiently calculate the Shapley values for structured additive regression models, or STAR models. A STAR model is simply a sum of partial models, each using only a few variables. The algorithmic complexity of StarShap is exponential in k, the maximal number of variables used by the partial models. For moderate values of k, the algorithm will be fast, and it is always exact. However, even though the computation time is exponential in k, our experiments show that StarShap can handle a surprisingly large number of interactions while still outperforming state-of-the-art Shapley value approximation algorithms. In this figure, vertical dotted lines represent the time StarShap took to calculate the exact Shapley values for some problem. The solid colored lines represent the quality of the approximation algorithm outputs for a given time budget. The lower, the better. Let's look at the vertical dotted line at just under 50 seconds. That's the execution time of StarShap on a model using 9 variables in each partial function. Given the same amount of time, the Shapley values returned by the approximation algorithm were of very poor quality, with a coefficient of determination below 0. We can conclude that StarShap can interpret highly complex models much better than approximation algorithms, as long as the model takes the form of a star model. Another important property of StarShap is the fact that its algorithmic complexity does not explicitly depend on the dimensionality of the data. We see in this figure that the computation time of StarShap remains constant, while approximation algorithms take increasingly more time. This means that StarShap is especially well adapted to datasets with very large numbers of variables. Imagine, for example, using StarShap to interpret climate models or genomic studies with thousands of features. To summarize, StarShap is a new Shapley value algorithm which works on a variety of models. This includes generalized additive models and sparse decision trees, which already had dedicated algorithms, but also generalized additive models with pairwise interactions, sparse polynomial regression, and any other model that can be written as a structured additive regression model. This includes star RKHS Weightings, which we introduce in this paper. This brings us to the second contribution of our paper, which is an expansion of the theory and applicability of the recently introduced family of functions, RKHS Weightings. An RKHS is a reproducing kernel Hilbert space. For example, the predictor returned by a kernel method, like a support vector machine, is an RKHS function. An RKHS weighting is a model whose output h of x is calculated as the expected weighted output of a base predictor. The weight function, alpha in the equation, is the RKHS function. This is similar to the well-known random kitchen sinks of Raimi and Recht, but the postulate that the weight function belongs to an RKHS adds many interesting properties to the model and allows elegant mathematical analysis. In this paper specifically, we show how to build RKHS weightings, which are structured additive regression models. This creates theoretically grounded, interpretable models. While these models did not outperform conventional models in our experiments, their performance was comparable. This shows that they are a promising model family and should be further studied. Thank you for watching. We hope our contribution will inspire further research in interpretable machine learning and theoretical model development. For any questions, you can contact me at my email address.